I would like to start with the title. So the title is Can we achieve 100% renewables? Flexibility options in the electricity system. And I would say that we would like to be a bit provocative in the title and to start introducing this kind of extreme scenario, mainly because we need to understand, by thinking at such an extreme case of 100% renewables, to understand what are the challenges that we are going to face in the future in a transition that we are now faced with towards higher levels of higher penetration levels of renewables in the system. The work indeed has been performed for a project with the European Copper Institute, and here we present key results, and further information can be found also in our report. So I will move on with the overview. So I will discuss on 5 key topics, and the one will be the definition of power system flexibility. I will move on to the need for flexibility in future power systems, and then I will discuss on an overview of flexibility options, and I will map these options on the key characteristics that they provide. And finally, I will provide the key conclusions and recommendations for how to include these options in the future. So starting with the definition of power system flexibility, I would like to take you back to, let's say, the key aspects of what is a power system. And a power system is actually the power systems are mainly designed to ensure the spatial and temporal balancing of generation and consumption at all times. This is the key aspect of electricity. And looking at it from this side, we can say that the system is more or less a set of areas that have some demands. The demands are placed somewhere into these areas, and they have different sizes. And on the other hand, we have supply, the electricity supply, and you can also see that not always the supply and demand matches the area where it is placed, and that's why we need networks that come in the middle of these areas, and they ensure that there is a transfer of electricity in order to match and to have this balancing overall. So if we make an overview, we can say that the system actually is the set of all the operational rules, how all this complex situation is operated. The demand is actually, most of the time, is considered non-controllable, but we could say that it's partly controllable. The supply could be controllable, but actually now we talk about new forms of renewable supply, which is non-controllable or intermittent. And finally, we have the network, which is actually provides the ability of the system to do this spatial matching. And keeping in mind, let's say, this definition, we can understand also the key definition of power system flexibility. And flexibility is actually represents the extent to which a power system can adapt electricity generation and consumption in order to maintain the stability in a cost-effective manner. And in other words, flexibility is the ability of a power system to maintain a continuous service in the face of rapid and large swings in supply and demand. Traditionally, flexibility was provided in a power system by the generation side. And that's why when we talk about measures of flexibility, we were always thinking on how fast can our power park follow the ramps or the changes into the demand. And that's why the key measures of flexibility have always been ramp rates or minimum up and down times, start up and shut down times. And these are kind of like key indicators that we can use for flexibility in order to understand how flexible the system is. And further, the power networks have an intrinsic role in flexibility, because these power networks are actually the key enablers of flexibility, because they will define actually how, which is the spatial dimension of balancing, how much you can extend, you can use resources from another area to balance problems in your area. So moving on, I will discuss a bit what is this transformation that we are facing and what is, let's say, the new need for flexibility. And I will start by showing you a typical profile of daily patterns of electricity demand. And as you can see, this is a typical demand we are talking about. This is 1 week. And as you can imagine, this, as you can see, we are absolutely predictable in the way we consume electricity. So we have the 5 first days, which are the days of the week, and the 2 days afterwards, which is the weekend, a slightly lower consumption. And I would say that this is how the world was, and this was how we designed our power systems until today. And I will try now to show you how is the world of tomorrow. So if we start increasing renewables, you will see actually I add a scenario of 20% of penetration of variable renewables, what we call like wind or solar penetration. This is a typical scenario that we did for Germany. And what we can see is that depending on when the variable renewables are feeding power into the system, we start to have a distortion of these kind of nice patterns that we had, and a gradual transition towards a shift towards down of this curve. Moving to a higher penetration level, we see that this distortion starts to increase, and that we have patterns that change between days. If we move to a more extreme case, to 60%, we start to see even this quite strange situation, if you see on the far left or on the far right, that the net demand actually starts to reach also 0 levels. And if we increase even more, then we see that actually we can reach situations that we have electricity demand or net electricity demand, which is the demand minus the variable renewables, that will become even negative. And if I isolate the two situations, let's say the nice situation of today where everything is in order, and the situation of tomorrow with high penetration levels of renewables, we can understand what is one of the key challenges on operation of power systems in the future. And this is actually the situation where we will need to operate a system following completely changing patterns and following ramps that you can see that are much more steep and follow totally different ways of operation. And this is actually what is one of the key challenges that arrive now in the operation of the systems. So moving a bit closer to on looking at what these ramps are, we provide this type of graph, and maybe I can explain a bit how this graph is can be read by you. So normally this graph is what we call hourly. This is a kind of like hourly ramping range of net electricity demand for different penetration levels of variable renewables. And what it shows actually, it shows for each point of this graph how many hours of the year we have these values of ramping. And further, it shows all the values that are above or left of this graph are actually the time of the year that there is more than this value, and the values that are on the right side is actually the time of the year that we have lower ramps than this one. Now, what we can understand and see clearly from this graph is that there is, starting from lower penetration levels, maybe we should just shift towards the left side of this graph, and we see that when we have low penetration levels, the ramping expectations in the system, the maximum ramping that we see is around, let's say, 7 megawatt. The more we add variable renewables in the system, then the ramping events are starting to increase. And this is now, we can see that when we go to an extreme scenario, first of all, while in the beginning we needed something like 7 gigawatt of ramping, maximum ramping, we have to move towards 25 gigawatt per hour. And this is an extreme increase. And furthermore, we can see that also in the negative axis, if we move towards the right part of the graph, we have the same trend. So the more renewables we add in the system, the more we need, we will be exposed to higher ramps, and the more so the need for flexibility starting to increase. So on the one side, we will have, let's say, the requirement for flexibility because of this change in the system will increase. But as a second point, let's see what will happen, let's say, to the power park. And we will show this by showing an example that we picked up from the operation of the power system in Germany. So this is actually, this graph shows you can see the demand curve. Again, it is a typical demand curve that looks the same, like I showed you before. And then you can see with different colors the different power plants and what is their, let's say, how they supplied the power in these hours. And this is a typical week on February in 2011. And as you can see, we have on the far down, we can see the exporting of the system, and this is limited, it's stable, but more or less limited. And then we have the nuclear power plants that are more or less stable. They cannot change their production a lot. And then we have the more flexible power plants on top of them. And at some point we see with green, we see wind, and with yellow we see the solar generation in the system. And what we can see is that actually what happened in this case is actually the situation that is shown here, where we have what we call an oversupply event. So we have a high penetration of wind, and this was combined with a situation of a low demand. This was in the evening of Friday to Saturday. And we reached the point where the conventional units were reaching their limit into ramping down, and but this was not enough. And this is a typical situation where we see that that the systems start to reach their limits, and then as a immediate reaction, we can see how the price of electricity started to go down, and then we had this event of having a negative price in Saturday. And this is a key message to see that the way that power systems were operated and designed is starting to be challenged. Moving to the next slide, we tried to make the same graph, and this is like what we call the full load hours for different penetration levels of variable renewable generation. And we see that this blue line on top is the situation without any renewable generation. And if you see, we have three lines which represent the base load, the mid load, and the peak load capacity in the system. More or less, the base load capacity represents what is the capacity of units that can be operated without changing their power, and this is, as you can see, exactly at the point where we have the far right point of this graph. And similarly, we can see what is the mid-load capacity of the system, let's say the relatively flexible power plants. And on the top, we have the peak power plants, which are the more flexible power plants, which have to supply for the peaking demand. Now, as we see, the more we have an increase of the variable renewable generation in the system, the more these curves, they start to shift towards down. And this shifting towards down, it creates an impact exactly to how this capacity can be utilized. So looking at, for example, at the base load capacity, we can see that their full load hours, the hours that they can be used, is reduced dramatically from a full load hour of a full year moving to a number of 1,000. And this the same starts to occur also for mid-load and also for peak load capacity. And this is a direct impact, and this shows actually that some of these power plants start to face problem with being economic. And a direct impact is several of these power plants, and starting from more expensive ones like peak load power plants, will not be able to participate anymore into the market. And this is a second let's say, result of introducing variable renewables in the system, that we start to have less conventional units in the system that they can finance themselves. And moving so to this slide, we can let's say put our thoughts together and understand what is now the new need for flexibility. So looking at the traditional power systems, the need for flexibility was actually to cover these small demand variations between days and between hours of the day, and mainly to cover some sudden loss of generation units if a unit goes offline because of a fault. So we would have what we call a variability of demand and some kind of uncertainty of supply. And then in this traditional power system, the flexibility was provided mainly from the supply side, and this was the power plant fleet. But with the introduction of variable renewables, we start to see this dual effect. On the one side, we have an increase in the need for flexibility because the variability and the uncertainty of the supply side is increased. And on the other side, we see that we have a reduction in the flexibility potential because the variable renewables actually displace a part of the conventional generation capacity, and this is actually a part of the conventional capacity that is needed in order to balance the systems. So a key message is that new flexibility options are needed in order to let's say, bridge this gap. And moving on this line of thought, we can start to see what are the impacts of variable renewables in the flexibility, what we call the flexibility timeline. And here I can say that this is actually how the operation of a power system will start to change in the planning. So looking how traditionally we were thinking on designing power systems was mainly that the key question was, do we have sufficient generation to meet the load? And this would start by looking far on studies that were years ahead and saying, okay, how we need to design our generation fleet in order to have sufficient power plants, until the day-ahead scheduling, intraday and balancing, with key question, do we have enough energy to supply the load? Now, when we look at systems with the high penetration level of renewables, we start to see these questions changing, and then the key question starts to become, when we see the long-term planning, we say, the key question is actually, does my system have sufficient resources to manage the operational variability? Will I be able to supply my system for example, with variable renewables between different seasons? And when we talk about operational planning and flexibility in this context, the key question is that how many flexibility resources should be committed so we have a secure operation in the day-ahead planning? And when we reach the balancing and the operational flexibility, the key question is, which are the most economic resources to balance the system for its operational time? And moving from this, we will discuss we will start the overview of the key flexibility options that we investigated. And on this, we will start with the categorization of the options. And looking on the different options, we should look along the areas of the system. So we identified the 5 key areas, and this is energy storage, demand, supply, network, and the system itself. And we investigated which options could be some good options for providing flexibility in the system. And this is, let's say, one first mapping. This is the overview of the options that we investigated. In total, we investigated around 20 options. And with different colors, you can see the options that belong to the different categories. So looking at supply, we would think of flexible coal power plants, gas power plants, oil power plants, biogas, CHP, nuclear, and one new option is actually the active power control of variable renewable energy sources themselves. And on this, it's actually the options of curtailment of variable renewables. Moving on the energy storage, the key options that we found are traditional pump storage, the compressed air energy storage, flywheels, batteries, and of course, and the hydrogen, which is like the power to gas option. On the demand side, we see demand response, and this is a big subject, and we saw 3 different, let's say, areas, which is energy-intensive industries, services, and smart applications. Electric vehicles and heat pumps, which is actually, let's say, demand that is joining together the electricity system with different sectors, like the transport sector and the heating sector, and also resistance heating, which is still in use in different countries. On the right side, we see the network, and the options actually for providing flexibility in the network is, on the one hand, is network expansion itself, so installing new lines, and there we can have the addition of transmission capacity, either AC, alternative current, or DC options. And on the other hand, by this we can increase meshing and alleviate congestions in the system. And on the other hand, there is also the option of including some smart devices, which are like power flow control devices, and these devices can allow a better use of the system. And finally, we have the system itself and what flexibility a system on its own can provide. And these are actually the incorporation of market rules that can allow flexibility to be uncapped in the system, and on the other hand, to enable larger areas by making a market integration, so expansion of markets and expansion of control zones. Moving further, I will discuss the key characteristics. In our projects, we made the full mapping of each of these options, and this is organized in specific fact sheets. And here I will try to provide an overview of the key characteristics of all these options. And this overview can be given in this graph, and I will spend a bit of time on this in order to let you understand what is all the information that is there. So on the on the x-axis, we can see the different time frames of flexibility. So starting from short-term flexibility, so real operational and flexibility that has to do with balancing in the terms of minutes or seconds. Then moving towards mid-term flexibility, so let's say flexibility that is needed for day-ahead planning of a system. And then on the far right, what is, let's say, the assessment of the technologies concerning the long-term flexibility, so looking at months ahead or years ahead. On the y-axis, we see all the different options that we investigated, and especially the options that are that include the storage, demand, and supply. And there we can see the different options in two categories. Red options are like options that are mainly small-scale distributed technologies, And bold and underscore options are actually technologies that are considered to be mature technologies. And if we look at the graph, first of all, we can see a key characteristic is that mainly the new options are options. Key new options are options that are small scale and distributed technologies. And these are like micro CHP, biogas, small scale demand resource vehicles, heat pumps, electric heating, flywheels, batteries. And these options, in order to be used, they imply that there should be a communication and control infrastructure, which is the key enabler to make them being useful for the system. Now, moving to the supply options, we can see that actually the supply options are key mature options, and these are because these were the options that were traditionally used in order to provide flexibility in the system. And we can see when we think about the impact of higher penetration levels of variable renewables in the system, we can see actually that the key effect when we look, for example, the midterm flexibility is that we expect that thermal power plants will need to increase their cycling. So they need to operate not so in a stable form, but actually to shut down and then start up in much more frequent cycles. And then in this respect, the operational availability of a power plant will depend on how how fast they can start and shut down, and what is actually the cost impacts of this. So in this respect, power plants like lignite and nuclear power plants, who are quite inflexible in providing this, are starting to be not so good options for such systems. And we see that key options that we can expect that will be used would be coal or CHP or combined cycle gas power plants or internal combustion engines, who are power plants that have much higher flexibility. Moving towards the demand side, we can see that that actually the key one option that is actually, let's say, a low-hanging fruit is the industrial demand response. Of course, it has a high potential, but its flexibility will be actually depending on the primary industrial process, and in this respect, it is constrained by this. On the other hand, again, when we see about small-scale demand response, again, we see a high potential, but again, this flexibility will depend on user behavior. And the same is actually for electric vehicles and heat pumps, since they have a big advantage that they do not form an option. This is not an investment for the power system in this respect, but their appearance will depend on other sectors. But on the other hand, they will be constrained by their primary operation. And when we look at storage, we can see that pumped hydro, which was traditional, this is one of the, let's say, the traditional options for storage. It is a very good option, but we find out that its potential for extra expansion is will be quite limited. On the other hand, compressed air energy storage, we can see that it is an option, but again, it will be restricted. It has a restricted potential for expansion, and also it is bound to a low efficiency. When we look on flywheels, flywheels could be an option when we talk about short-term flexibility, but not they would not be applied to provide serious options for midterm flexibility. And that's why we can see that the graph is actually more dark on the left side. And looking at batteries are a good option for short-term up to mid-term flexibility, but still some technology development is needed and some efficiency improvement. And finally, looking at power to gas, if we look on the far right of this graph, we can see all the, let's say, where we see long-term flexibility options. And power to gas is actually the only option that can be compared can be an alternative option to the supply options. In this respect, actually, power to gas is a technology that transforms electricity back into a fuel, to gas or hydrogen. And however, this is in the expense of high losses. And it will be economical probably in systems with very high shares of variable renewables, that when there is a lot of events, of oversupply events, that these power to gas technologies can be used to produce fuels that can be then used in some other period of the year. So this is, let's say, the overview of the options. And a general remark is that we see that that there are options. There are different options that can be applied in different time frames, and then it is key to understand how to enable these options to come out and to compete in order to have a system that will be more balanced on the provision of flexibility. So I will move to a short discussion on what we think about some key market barriers, and explaining what is the debate between, let's say, incentivizing power plants, conventional power plants, and incentivizing flexibility. So in this graph, we see on the left upper side, we see the different, the three, let's say, key technologies and their cost divided by, let's say, their cost rates, their costs, euro per kilowatt. And we see that peak load technologies have higher costs, and that's why the slope of this cost curve is higher. And we see that mid load technologies have lower slope, and base load technologies have even lower slope, but they have different starting costs. So this is actually on the slide, on the graph below, we can see this effect of how the residual load curves are pushed down because of the impact of different penetration levels of renewables. And by looking how these the different technologies actually will be placed into the merit order, we can understand how the different the three key technologies will be represented into the final energy mix. And there we see that if we have zero penetration level, we have a typical situation where we have high base load energy, high level of the energy provided by base load power plants, and then we have a part provided by mid load, and then a smaller part by peak load. And then moving towards more variable renewables, we see that the share of base load technologies is unavoidably reduced, and that peak load power plants will have to take a higher responsibility, let's say, in the system. And then this means actually that still conventional peaking power plants will be needed in order to meet the load in times of these low variable renewable generation hours. And the key question here is actually how could we incentivize flexibility. And a key thing to remember is actually by thinking that supply options are driven by market prices. So when prices are higher, then it is better for traditional power plants. On the other hand, flexibility options are mainly driven. The investment flexibility options is driven mainly by market price variability, and this is like spreads. And then, however, the market prices and spreads are related to each other, making intervention to the supply side have an impact to the role of other options. So if we try to keep more capacity, conventional capacity in the system, then prices are actually reduced. That's a situation that we see often. And by seeing lower prices, we cannot see also the spreads are also reduced. And this means that there is not enough incentives to provide new options like demand response and energy storage. And this is, let's say, all the decisions that are taken compared to how to keep base load or mid load technologies into the system affect the transformation to the system. So towards a future structure with more flexible power plants. And finally, I will shift towards our conclusions and recommendations. And I will start with one graph that is what we call the flexibility gap. And this is, I think, something that is important to remember. And we can see in the x-axis, we see how increasing penetration levels from low to high, and on the y-axis, we see the system flexibility. So we starting from a level of low variable renewables. The flexibility needed is relatively low. And moving towards higher levels of flexibility, we need more flexibility, and this creates this this flexibility is actually provided currently by the supply side, and this is the green area. And as we can see, this green area, as we discussed, will be reduced because of the impacts to the supply side. And this means that this traditional supply flexibility, by reducing this traditional supply flexibility and increasing the flexibility needs, we have a flexibility gap that is starting to evolve in the system. And this gap has to be covered by the use of new supply flexibility options, of storage flexibility or demand flexibility. And what will be the relative position of all these options will depend on how they will compete in the market. And what is very important is to allow that all these options are able to enter the market and to compete in order to find a position. And let's say we try to put all the key ideas into one slide, and here we can say, okay, the first one is actually, the first conclusion is that this flexibility gap is created by this shift towards a high variable renewable system. This is something to expect. And a second key result is that the new flexibility options are distributed options, and these are in demand and storage options. And these options actually require control and communication infrastructure in order to be uncapped. Another key result is that when we talk about variable renewable energy sources, we need to think that controlling variable renewable energy sources is unavoidable for higher penetration levels of renewables. So it means actually that it is probably in many cases when we move to higher variable renewable cases, we will have a better option to curtail renewable energy than providing flexibility from other sources. And However, this is an important aspect that will face a lot of institutional, perceptual, and potential political challenges. And finally, for sure, there are a lot of challenges in order to change the market to reduce this flexibility gap, and key options like changing the minimum bid size into market, reducing the bid size, or reducing the scheduling periods and the gate closure times will allow more options to participate. And furthermore, we see that we need more incentives and systems for demand-side management. And even though we identified that there are options that are, let's say, low-hanging fruits, they still need, the market needs to be prepared for them. And finally, one of the key no-regret solutions is to extend the market side. And this can be done either by grid extensions on the one side, or changing the market designed options to enhance international trading and make use of differences in adjacent markets. And by this, I would like to thank you, and I would like to take questions from your side.
Okay, thank you very much, George.